In this tutorial, I will show how to implement a simple throttling application in the chemical machine. I will also compare this very briefly with implementations in Akka and other concurrency libraries. The throttler is a functionality that will limit emitting a molecule. Generally, if you have any kind of signals that can be sent at will, throttling these signals means that you will delay them so that during a certain time, not more than a certain number of signals are sent. In the chemical machine, the only way to send any signals is by emitting a molecule. Therefore, throttling in the chemical machine means that we will limit emitting a molecule. But how can we do that? Suppose we have some molecule, say S. It already exists, it is defined, bound to a reaction site, and has some reactions defined for it. External code might want to emit that molecule. How can we throttle external code? Well, we cannot directly do that. Instead, we can produce a new molecule. We can define a new molecule, say R, that external code now needs to use instead of S. Emitting a molecule R would mean a request to actually emit a molecule S. And so we will give R instead of S to external code. The value carried by R will be the same, of the same type as that carried by S. So the external code will just need to change their emission of S to emission of R. And we want this automatically to throttle the resulting emission of S, so that the molecule R could be emitted at will by external processes, and somehow this should cause S to be emitted at a limited rate. Defining this more precisely, I would say that no S molecule may be emitted until at least a given number of milliseconds, delta t, has elapsed after any previous molecule S was emitted. So a typical pattern for implementing such a thing in the chemical machine is to implement a function that takes a molecule emitter and returns a new molecule emitter. A function such as this one. It will take a molecule emitter S that is previously defined and already bound to some reactions. It will take the delta t value and it will return a new molecule emitter. The code of this function would look roughly like this. We will define a new emitter. The type A will be the same as here, so we will define some reaction, a new reaction for this molecule R, and we will return R, the emitter for the new molecule, as our result value in this function. So what remains is to define this code, and maybe other code that needs to be here. Let us reason about what this reaction should do. This reaction should consume R of x, and since R of x is understood as a request to return S, we should decide whether we return S or not, whether we emit S rather, not return, whether we emit S or not. So we could imagine that a reaction would decide that using some condition, such as this one. And if the condition holds, then we emit an S. And if the condition evaluates to false, that means the request was emitted too soon, and it cannot be automatically fulfilled. In that case, we would have to delay the emission of S until a suitable later time. But until when? This reaction would start automatically when external code emits many instances of R. And so this reaction could not possibly know about other such reactions that are also trying to determine whether to emit S or not. So this reaction does not have enough information actually to decide this. So this wouldn't work, this kind of idea of having a condition. Actually, we need to prevent this reaction from starting until appropriate time has elapsed. But the only way in a chemical machine to prevent a reaction from starting is by withholding some input molecules that this reaction requires. So R is an input molecule that external code will emit. The only way we can have any control over starting this reaction is if this reaction has another input molecule that we control. Therefore, we must have another input molecule in this reaction. Let's call this input molecule allow. So now imagine that the reaction would have this code. It will consume allow. It will also consume R of X. And it will immediately return, it will immediately emit S of X because we allow its emission. So the allow molecule, if present, it means S of X can be emitted right away if a request comes. But then, after that has been done, the next request, R of X, cannot be processed immediately. At least the time delta t milliseconds needs to elapse. So we cannot emit allow in this reaction right away, but we do have to emit allow at some point. Otherwise, this reaction will never start again. So we need to delay emitting allow. So that's a very simple way of doing that. We emit S, then we sleep for the delta t milliseconds, and after that we emit allow. And after that, another reaction can start, consuming another R, this allow, and doing the same thing. So this actually is sufficient to implement the functionality we want. This is now a first implementation of the throttle function. We need to define the allow molecule. We need to emit it initially. So this allow molecule is present when external code starts to emit R. And then we return this R. So now, in principle, we're done. That's the solution, 6 lines of code. Let's discuss a little about using thread sleep. Now this is blocking the thread. This is not great. We're blocking the thread. We would like to avoid that maybe. Now in this case, actually we see there will be only one copy of allow in the chemical universe, or at the reaction site rather. At the reaction site where we define this, there will be only one copy of allow ever. And so there will be only one reaction running at any one time, one of these reactions only. So actually this entire site could be single-threaded with no degradation of performance, or even with an improvement of performance. So it's okay that this thread is blocked. There will be only one thread blocked at most, and we don't lose any parallelism due to that. alternative implementation would be to have a timer, say a Java timer, which we will use to schedule emitting this allow molecule. That can be done, but the timer will statically allocate a thread to itself, and that thread will be blocked a lot of the time, perhaps. So we still would have a blocked thread somewhere else. It's not necessarily a good solution. And then timer would require us to keep track of it, to create it, and to maintain it. So it will complicate the code. So perhaps this straightforward implementation is adequate in the current situation. We can still improve it in two different ways. First, we notice that allow is always present. It's consumed and then it is emitted again. So there is only one copy of it present, and then reactions always consume and emit that copy. This is the pattern that I call static molecule. It's a molecule that is kind of always present, and at most one reaction can consume it. It's kind of a singleton molecule, or a static molecule as I call it. The chemical machine in the chemist library has a special feature for declaring static molecules, and then it will check your codes that you don't forget to emit a static molecule. So that will, for example, if we forgot to emit this, or if we forgot to emit this, this code would not work. And declaring it as a static molecule would avoid those errors. The second improvement could be that we use blocking idle annotation on, well, not annotation, it's a function call, around the sleep. And that would improve parallelism for this reaction site. Now, this reaction site really is single-threaded, but we could imagine different situations when we have to reuse a thread pool, and this could be hurting somebody else's parallelism. And so this is the final code. The blocking idle is used around the thread sleep, and allow is now a static molecule. That is the syntax for defining static molecules. And so now this would be a good implementation, perhaps, of Throttle. Another kind of more industry strength implementation would be to control the thread pool on which this site is created. So that would be another argument here, perhaps, or something else. Let's test this now. To test this functionality, we define a reaction that prints the time that has elapsed since the previous run of that reaction. So that would be easy then to see whether throttling correctly works. Let's define a function that creates such reactions. So this function will create a reaction that takes a timestamp molecule and a signal molecule S. And this timestamp molecule carries a long value, which is the timestamp in milliseconds. And the signal molecule is just a unit valued molecule for this simple example. So the reaction will consume them and then print the time interval that has elapsed since the previous run of this reaction, and emit a molecule with a timestamp of the current time. So that's for the next run of this reaction, this will be the timestamp here, and then we will subtract the new current time, and so on. So that's how this reaction would work. Initially, we will emit timestamp with 0. Well, we have to emit initially. Well, in this reaction timestamp is also a static molecule, actually. So I could make that explicit. So that things are checked statically also for static molecules. Possibly optimized. So now let's run a reaction without throttling and with throttling. So we just create a molecule S, which is this print elapsed with the message unthrottled. And then we emit 10 molecules S. Now S, as you see, is just a unit molecule, so it's not carrying any value, it's just a signal carrying a unit value. Let's run this and see what it prints. Right, so the first timestamp is here because we subtract 0, because the initial timestamp value here is 0. And after that, we see there is 0 or 1 milliseconds between invocations of the reaction. Now let's run a test with throttling. Let's take 200 millisecond interval for throttling. So that means we will still emit the R molecule quickly, 10 times, but the S molecule will be called at 200 millisecond intervals or longer. So any call to S will be delayed so that the throttling happens. In the test, we still need to wait because the test system would terminate and we won't see the output. This is a very simple test, so I'm just printing it to the standard output and look at the results. So let me run this. So now you see they run with about 200 millisecond delay. So this concludes this little tutorial on the chemical machine. We implemented a generic throttle function that transforms one molecule into another. And it's about 10 lines of code, the throttling function, which is already with some formatting and lines like this. And the first implementation was just 6 lines of code. It still works, just less hardened, so to speak. And just briefly, I'd like to compare this with how throttling is implemented in other concurrency systems. So recently, Adam Varsky made blogs about comparing Akka and Scala Z concurrency. And one example in these blog posts was a rate limiter or throttling function implemented in various frameworks, in Akka, in Monix, which is also a streaming and task framework, and in ZIO, which is a Scala Z effect library. This is the code that you can see using Akka. So it's a rate limiter using different frameworks. So for example, Scala Z code that would look like this. So there is some rate limiter that is defined here and implemented, and so on. So if you exclude empty lines and comment lines, this is maybe about 30 lines of code or so, maybe more. So this is the blog that I was talking about. I encourage you to read it. It's a very useful comparison, which comes in 3 parts. So this is the first part, and you can easily find the next parts. The comparison between Akka and Monix and Scala Z is not really a apples to apples comparison, so to speak, as the blog surely points out, because Akka is a general concurrency framework that can implement arbitrary concurrent and parallel processes, whereas Scala Z effects, ZIO, and Monix task are not general purpose concurrency libraries. They have much narrower set of possibilities and scope, and it's not fair to compare them since they are specialized for different problems, different classes of concurrency situations. Nevertheless, it's interesting to compare that each of those other frameworks require about 40 lines of code, excluding imports and comments. Additionally, about 30 lines of common code in this queue implementation. And Akka typed needs about 35 lines of code also instead of 40. So this is to contrast with about 6 or 10 lines of code in the chemical machine. And the chemical machine code in comparison is much more declarative and concise. We derived this code more or less logically from first principles, from systematic reasoning about what molecules should do and how we could control the concurrent process. This program is obviously correct in a sense, because we can visually reason about the presence of these molecules. For instance, somebody emits R, we already have an instance of allow, so this can start, this will run, this will emit S, so that will run the reaction, whatever reaction S will start. Then we wait for the given interval of time, and then we emit the allow molecule. Until then, no other instance of this could run, because there is no more allow, and we guarantee that with just one emitting just one copy of the molecule allow. And so this is obviously correct. This is exactly the behavior we want. We just say, well, we allow emitting S only after this interval. That's what this program says. It doesn't say much more. It doesn't define auxiliary classes or, stop functions, start functions, or anything like this. So that's why it's declarative, and these implementations are not declarative. They run things and fork, and this is much more low level. This is much harder to do. You need to know and understand much more about how these things work in order to write this program. You see, there are 7 different steps in this, run queue and so on. This was the ZIO, and the Monix implementation is a bit similar. Also, you do various things like this, and queue 1, 2, 3, 4, 5, 6, 7. Akka is again, so you create promise, lazy future. You need to know all of this. You need to know all of these. So you create this Akka rate limiter, then rate limiter actor, then you define all these functions. You need to implement all this functionality just so that things work. And that is the antithesis of declarative. you implement things that have nothing to do with your problem, because otherwise nothing will work. And so you implement a lot of auxiliary functionality that has nothing to do with the formulation of your problem. And if you contrast this with this code, this basically formulates the requirements. This one line is your entire code that formulates the requirements. Everything else is declaration, really. This comes along with this. So these two lines, maybe, is the real core of the 6-line program that we have written. Everything else are just declarations. And this line, together with this one, directly expresses the requirement. We can allow emitting S after a request, but only after this much time has elapsed. So this concludes a little tutorial about throttling and rate limiting in the chemical machine.